Welcome back to the laboratory, everyone. In our previous lectures, we explored the architecture of infrared spectrometers. We examined the Michelson interferometer, FTIR instrumentation, single beam and double beam systems, and even older dispersive spectrometers that preceded modern FTIR technology. But no spectrometer can function without two absolutely essential components. One, a source that generates infrared radiation, and a detector that measures it. Today, we are going to focus entirely on these hardware components, specifically infrared sources and infrared transducers, also known as detectors. Before we discuss individual source types, let us discuss a basic question: why do we even need a specialized IR sources? To study molecular vibrations, we must expose molecule to infrared radiation across a broad range of wavelengths. The source must therefore emit continuous, stable, and sufficiently intense infrared radiation. Most infrared sources work on a very simple physical principle: heating materials to high temperature until they emit thermal radiation. This essentially black body radiation. Any object above absolute zero emits electromagnetic radiation. As the temperature increases, the intensity and spectral distribution of the emitted radiation change. By carefully selecting materials and operating temperatures, we can generate radiation appropriate for specific IR regions. Now let us examine the major infrared sources used in spectroscopy. The mid-infrared region is the most important region for the molecular spectroscopy, typically spanning 2 to 15 micrometers. This is where most molecular vibrational absorptions occur. The first classical source is Nernst Glower. This source consists of rare earth oxides formed into a ceramic rod. When electrically heated, the rod emits intense infrared radiation. The Nernst Glower typically operates between 1200 to 2200 Kelvin. This extremely high temperature produces strong IR intensity. Its advantages is high radiation intensity. This makes it useful for many spectroscopic applications. However, the material is not electrically conductive at room temperature. It must be preheated before normal operation begins. This makes startup more complicated. Another extremely common issue with the source is the Globar. A Globar is Another extremely common source is the Globar. A Globar is a silicon carbide rod heated electrically. It typically operates between 1000 to 1500 Kelvin, slightly cooler than the Nernst Glower. The Globar is mechanically robust, stable, and reliable. It performs particularly well at wavelengths below 5 micrometers. Because of its stability and durability, Globars became widely used in commercial IR spectrometers. Another simpler source uses nichrome wire. This is essentially heated metal filament. Nichrome sources are inexpensive, long lasting, and easy to operate. However, their infrared intensity is lower than Nernst or Globar sources. Now let us move into near IR region, approximately 0.78 to 2.5 micrometers. In this region, a simple tungsten filament lamp works extremely well. This is very similar to the filament used in incandescent bulbs. Because tungsten operates at very high temperature, it emits strong radiation in the near IR region. Now let us move toward the far IR region beyond approximately 50 micrometers. At these long wavelengths, ordinary thermal sources become relatively weak. Instead, we often use mercury arc sources. These are plasma-based discharge sources. Electrical excitation of mercury vapor generate strong far IR radiation. These sources are especially useful for far IR spectroscopy. Now let us discuss one of the most important modern developments, that is lasers. Lasers produce highly intense, coherent and monochromatic radiation. This allows extremely precise spectroscopic measurements. A particularly important IR laser is CO2 laser. This laser operates primarily in the 9 to 11 micrometer range. CO2 lasers are widely used in remote sensing, atmosphere monitoring, pollutant detection, industrial processing, and high precision spectroscopy. Because the wavelength is tunable, these lasers are excellent for selectively probing specific molecular absorptions. Now that we understand how infrared radiation is generated, let us examine how it is detected. The detector on transducer converts incoming infrared radiation into a measurable electrical signal. Without the detector, the spectrometer would no way to interpret molecular absorption. Infrared detectors generally fall into three major categories: pyroelectric detectors, photoconducting detectors, and thermal detectors. Each operates using a completely different physical principle. Pyroelectric detector. Let us begin with the most common detectors used in modern spectroscopy systems. These detectors are standard in most routine FTI spectrometers. The most common pyroelectric material is triglycine sulfide, commonly abbreviated as DTGS. Pyroelectric materials possess spontaneous electrical polarization. When infrared radiation hits the crystal, its temperature changes slightly. This temperature change alters the polarization of the material, and that changing polarization generates an electrical signal. The biggest advantage of pyroelectric detectors is the speed. They respond extremely rapidly to changing radiation signals. This makes them ideal for FTIR spectroscopy, where the interferogram changes continuously as the mirror moves. Another major advantage is that DTGS detectors operate effectively at room temperature. No cryogenic cooling is required. This makes them simple and practical for routine laboratory use. However, there is an important limitation. If the detector temperature rises above its Curie point, approximately 47 degrees Celsius, the material loses its polarization, and once polarization disappears, the detector stops functioning properly. Now, let us move to another extremely important detector category, that is photoconducting transducer. These detectors rely on semiconducting materials. Differ, Different semiconductors are used for different spectral regions. For example, lead sulfide is commonly used for near IR detection. Mercury cadmium telluride, commonly called MCT, is widely used for mid IR and far IR detection. When infrared radiation strikes the semiconductor, electrons gain energy and move into conductive states. As a result, electrical resistance of the material decreases dramatically. We measure this resistance change as an electrical signal. Photoconducting detectors are extremely sensitive, very fast, and excellent for high speed FTIR measurement. They are also widely used in gas chromatography IR systems and advanced analytical instruments. But there is a major challenge. These detectors are extremely sensitive to thermal noise. To reduce noise and maintain sensitivity, they must be cooled cryogenically. MCT detectors are typically cooled using liquid nitrogen at approximately 77 Kelvin. Without cooling, thermal excitation would overwhelm the signal entirely. Now, let us examine the oldest class of IR detector, that is thermal transducers. Unlike pyroelectric or photoconducting systems, thermal detectors simply measure the bulk temperature changes caused by the absorbed radiation. A thermocouple consists of two different metals joined together, for example, bismuth and antimony. When one junction heats up due to infrared radiation, the voltage difference develops between the junctions. This voltage is proportional to the temperature difference. Thermocouples are cheap, simple, and rich, but they are also slow and relatively insensitive. Typical response times are around 30 milliseconds, which is far too slow for many modern FTR applications. To improve sensitivity, multiple thermocouples are connected together. This arrangement is called as a thermopile. The voltages add together, producing a stronger signal. Finally, let us discuss one of the most sensitive thermal detectors, that is bolometer. Bolometers are made from materials such as platinum, nickel, and semiconductor thermistors. When infrared radiation hits the material, its electrical resistance changes. This resistance change is measured electronically. Bolometers are highly sensitive in the extreme far IR region. They are widely used in astronomy, space instrumentation, and far IR research. However, bolometers are required extraordinary low operating temperatures, sometimes as low as 1.5 Kelvin. This often requires liquid helium cooling. Because of this complexity, bolometers are rarely used for routine mid-IR spectroscopy. Let us summarize today's lecture, in which we have learned infrared spectroscopy requires both infrared radiation sources and infrared detectors. Common IR sources include Nernst Glowers, Globars, nichrome wires, tungsten lamps, mercury arcs, and modern lasers such as CO2 lasers. Infrared detectors fall into three major categories: pyroelectric detectors, photoconducting detectors, and thermal detectors. Modern FTI systems most commonly use DTGS or MCD detectors because of their speed and sensitivity. In our next lecture, we will move into one of the most practical aspects of infrared spectroscopy: sample preparation techniques. We will learn how solids, liquids, and gases are prepared for accurate IR measurements, and why proper sample preparation is absolutely essential for obtaining clean, reliable spectra. Thank you for watching, and I will see you in the next lecture.